now that we've seen quite a bit about Laplace transforms, we'd like to be able to try and simulate them or try to understand how to evaluate the Laplace transform and examine the pole zero diagram and so on and so forth using MATLAB. So we'd like to be able to use the system toolbox to implement rational transfer functions, visualize the pole zero diagram, the impulse response, and the frequency response. So we're going to use the following two systems in the next couple of examples to illustrate basically these two LTI systems. So we have h1 of s, we can factorize this into s minus 3 over s plus 2, s plus 3, and then this other one which is going to have complex roots. Right, and you can use the quadratic formula to find that, so we're going to get minus 3 plus minus square root of 9 minus 36 divided by 2. So we're going to get minus 3 halves. So we're going to get the square root of minus 27. So that's 3 square root of 3. So plus minus 3 halves square root of 3j. Something like that. So from these two, you can probably compute, hopefully by now, you can compute the impulse response. So I recommend doing that so that you can sort of try plotting the impulse response that you got computationally, algebraically with what you're going to be able to see computationally. And that's an exercise that's worth doing to build your intuition and sense of how the computation and the algebra and the sort of visualization interact with each other. So there's a conveniently named TF for transfer function in MATLAB. And what you pass to it is a numerator and a denominator. So and that's for your rational Laplace transform. And in particular, you're passing the coefficients of the numerator and denominator. So, for example, for our first system, this is going to correspond to s minus 3. So it's a 1s minus 3. And this is going to correspond to 1s plus 5s plus 6. And this is correspond to s plus 5, 1s plus 5, and this is 1s plus 3s plus 6. Right, so we're putting the coefficients, s squared over here. So we're putting the coefficients in descending order for the degree of s, and then you can just use TF to do this, passing it the numerator and the denominator. So we can construct our two systems this way. If you do it in MATLAB, you should see it pop out. Here's a system object, and here is its Laplace transform, and it'll give you the algebraic expression, the rational Laplace transform that we had on the previous slide. So I recommend actually doing this and having MATLAB open while you're doing this to try and watching this to try these things out on your own to get a feel for how they are going, how things work. So if you want to plot the impulse response, there is a other conveniently named function impulse, and so you pass that the system object, the actual the system object, which is the thing you constructed in the previous slide. So you pass it h, and you also pass it t. So this t is the time over which you want to evaluate the impulse response. So the default time axis that it uses is something like 3.5 seconds. I'm not sure why that is important, but when we're using the impulse function, you should actually pass it explicitly the time axis, because you want to keep track, remember, of the sampling rate fs that you're using to simulate your CT system in discrete time, so that you want to make sure that you keep track of the time axis yourself, because that might become important later. So just get into the habit of maintaining the time axis as a variable. So here we can do this here. We're going to set a sampling rate of 10 to the 5, which is 100 kilohertz, and then we're going to create our 5 seconds of time. Then you can use the impulse function to evaluate this first system h1 over time, and it's going to return the value of the impulse response and the time. So we make a figure, then we plot the impulse response, so we plot, the x-axis is going to have t and the y-axis is going to have h1. And then we can label, of course, always label our plots, and then we should be able to see the impulse response. So here we are. Here's the impulse response for our first system. It has two poles, and as you can see, it has a transient response, and then so this is over here is the transient, and the steady state value is 0. Steady state value is 0. If we look at our other system, this is going to have some complex roots, so it's going to have a cosine or a sine in it, and sine function in it, and indeed we see this kind of oscillatory behavior where it kind of goes up and down, and then actually it's going to keep wiggling at a very slow rate all the way through time. So its steady state response is zero asymptotically, but it's still going to it still technically has a little bit of a wiggle from the cosine. So what about the pole zero diagram? You can get the pole zero diagram by using pzplot. There's also, I think, pzmap, another function. You can use the help in MATLAB to find that for you. What it does is it plots the pole zero diagram, but it kind of plots it in this weird, skewed sort of way that doesn't really give a good, doesn't look right. You can see what it looks like just by running pzplot on its own. But if you want to kind of clean it up, you can use these 4 lines here, where you basically grab the line object that's inside the plot, and then set the markers. And the line object, it's not really a line; it's the it's the X's and O's from the pole zero diagram. So that's the marker size. So we change that marker size to 9. And if you want to make the markers a little bit thicker, then you can do that as well, and so they become a little bit more visible. So that's useful, I think, in terms of just visualizing things, and especially when you're trying to show these plots to other people. And this last line makes the axes have the same aspect ratio. It sets the aspect ratio to have equal axes, so that again makes it a little bit easier to visualize because the units are kind of to scale. So let's see what that looks like for our two systems. So here we are. We have our 2 poles for our first system at -2 and -3, as we expected from factorizing this denominator. And we have a 0 over here at s equals 3. So that's exactly what we expected to see. So now we can see at -0.5 for the other system, we indeed have 2 complex poles with the real part is -3/2 here and here. And then over here we have a 0, so we have a pole here and a pole here. And we have a 0 over here somewhere around exactly at -5. That comes from this numerator term here. So again, this pole zero diagram is exactly what we'd expect after having done the algebra. But it's easy to, you can then kind of just visualize, if somebody gives you a rational transfer function, you can just visualize the pole zero diagram in MATLAB to get a sense of what's going on. So the last thing we want to look at is the frequency response of the system. And remember, the frequency response is what we look at when we put in a complex exponential into an LTI system. And remember, because complex exponentials are eigenfunctions of LTI systems, if you put in a complex exponential, you're going to get back out the same complex exponential, but multiplied by a complex coefficient. That coefficient we called h of j omega naught when you pass in a frequency omega naught. And this frequency response of the system is just this this integral here, which, if you actually look at it, is the Laplace transform evaluated when s equals j omega. So that explains this notation. This notation is consistent with the Laplace notation, right? So we're emphasizing the connection between the Laplace transform and this frequency response, which turns out to be the Fourier transform, by using this h of j omega notation. So this is just evaluated. So this is just h of s on the imaginary axis, right? So it turns out that if we want to understand the frequency response, we basically have to slice the h-plane. We have to look at the slice of the Laplace transform at the imaginary axis. And so we can try to visualize that to get a sense of what's going on. So if we input a cosine, we're going to get these two, the cosine is going to get multiplied by a magnitude and a phase shift. It's going to have a phase shift. So we want to look at the magnitude and phase of the frequency response separately, and we want to understand what's going on with each of them. And in particular, we're going to focus mostly on looking at the magnitude of this LTI system. And so, because what we're thinking of is, okay, we pass a cosine in, it goes like a beep, right? It's at some tone, and then at that frequency omega of that beep, whatever it is, that omega naught, that's the frequency of that beep. So maybe it's 2 pi times 440 for 440 hertz. If h of j omega naught is small and the magnitude is low, that thing is going to get attenuated. And if it's high, it's going to get amplified. And so this is, in fact, exactly how to think about amplifiers or stereo equalizers, for example. So they're shifting in magnitude. If you pump up the bass on your stereo equalizer, you turn up the bass volume. That's actually doing something, putting it audio through like an LTI system, which is going to boost the low frequencies. Right. So the phase part actually represents the sort of distortion that the signal receives, because basically, if we had a linear phase, then that is that h of j omega is proportional. Proportional omega is a linear function of omega. This turns out to be just a pure delay. So if we had so if all frequencies get delayed the same amount, linear phase was great because basically everything is getting delayed by the same amount. However, if different frequencies are getting delayed by different amounts because of the phase is different for each of these different frequencies, you're going to get some distortion in the signal. There's going to be some bleeding or spread. So that's a topic better addressed a little bit later. So we can use the Freaks function to plot the frequency response. If you want to just get the frequency response, and unfortunately, due to some vagaries of MATLAB, you don't actually pass it the system object h. You're going to pass it the numerator and denominator explicitly. So you pass it Freaks the numerator and denominator exactly like this, and then you get this plot where the magnitude is plotted on log scale. So the frequency axis is log scale, and the magnitude of the frequency response is also log scale. And if you wanted a dB scale, because dB scale is also log scale, you can use Bode or Bode h of h1 as using the system object this time to produce a Bode plot. And you hopefully have seen something like these before, but this is how you get it in MATLAB. So the phase, for some reason, is plotted in degrees on the vertical axis against radian frequency, and this makes no sense to me. It's always kind of weirded me out. But there you have it. It's somehow, this is the default that engineers use. And there are some good reasons for it, but it somehow, to me, hampers understanding of what's actually going on. Okay, so let's look at what happens when I plot the frequency response. Here, notice if you use the Freaks function, it's going to produce a plot, and you might want to use the same trick we did before to kind of grab the line object and make it a bit thicker. I didn't do that here, so you can see these lines are pretty thin, but we can see this frequency response of h1. So what is it doing? It's the magnitude is staying kind of flat for a while, and then it decays off, right? So in some sense, we can think of this as allows low frequencies go through and attenuates higher frequencies. And as far as the phase goes, it is what it is, and you can see that it's mostly it's not quite linear, but it's not doesn't look too horrible. What about H2? Our system over here, H2. So this also is flat for a while. So it's also passes low frequencies. And in this case, the gain is with gain almost 1. Right, 10 to the 0 is equal to 1. And then it drops off and attenuates lower frequencies. The downside here is that the phase behaves a little bit, more nonlinearly. So we have this kind of backwards S shape for the phase, and that's kind of important to look at because even though this is kind of flatter for a longer range of frequency, it has maybe the phase characteristics might make it less favorable to implement or use in a real system. So you can also compose systems. So you can cascade systems. You can put one system after another. So that is, in the time domain, you would be saying take x. If you put in input x, you'd take x of t star h1 of t star h2 of t. But then these two things convolved with each other, the h1 and h2, in the Laplace domain correspond to the product, because convolution in time is multiplication in the Laplace domain. So we can take an overall system H3. So again, the picture is H1, H2, and then you're basically drawing a little dotted box around this and calling this thing H3. So this H3, you can multiply these out, and if you multiply them out in MATLAB, you just say H1 star H2, you'll get a transfer function that looks like this. And I literally just copied this off of what I got out of MATLAB because I didn't want to bother multiplying out everything. Unfortunately, what MATLAB returns, if you want to actually get the numerator and denominator, because you might need that again to use freaks, so we need this. So we need this for freaks. We need the numerator and denominator. You have a kind of type mismatch in MATLAB, so you have to convert. It returns cells. You have to convert the cells to arrays. So to matrices. So you convert the cell to a matrix, and then you're back in business. Now you have the numerator and denominator of these two systems. Of this system rather here, the product of these two systems. So then we can plot the impulse response, pole zero diagram, and frequency response, just as we did before with the individual systems. So here you can see the impulse response here looks like a combination of the two impulse responses, and in fact it's the responses of H1 and H2. And when I say actually combo, I should really say convolution. Right? This is in fact this is the looks like it can get crossed off and say is, right? So this is the convolution of the two impulse responses of H1 and H2, right? And here we can write it out in factorized form. This is the overall transfer function. So now we can look at the pole zeros. We're going to get a combination of the poles and zeros from both of the two systems if we do the pole zero diagram. And lo and behold, that's exactly what we get. We have a 0 at 3 and a 0 at -5. Then we have poles at -2 and -3. And then also these two complex poles at minus 3 halves plus minus square root 3 times 3 halves j. So we get exactly the pole zero diagram we expect from taking the product of these two systems. As far as the frequency response goes, remember both of the frequency responses were flat for low frequencies, so we still get flat frequency response at low frequencies with this tail off. Now, remember the flat part was wider for the system 2, so shorter in system 3, and so shorter in system 1. So in system 3, system 1 kind of dominates and says, okay, we're only going to be flat for this shorter length of time. And the phase looks pretty nice. It looks very much like the phase of system 1. So as a do-it-yourself opportunity, try any of the systems that we've taken in the previous sets of slides, any or transfer function that you've seen in the homework, and then try and use MATLAB to plot the impulse response, frequency response, and pole zero diagram, and then you can get a sense of what do these systems look like, and building that kind of mental picture of what a impulse response looks like for a given Laplace transform. You can do it. You can say I know what it's going to be algebraically, but getting a sense of what that looks like in a picture can be really helpful. Another thing is the cascade that we talked about before is a series combination of systems, but you can also think about systems in parallel with an adder, a summer at the end, and then you can also just use the plus sign in MATLAB to add two systems. So why don't you try adding H1 and H2 and then seeing what happens to the pole zero diagram and the impulse response and the frequency response. So this again is you think of this MATLAB here as being like a little playground for you to play around with the different systems that you've seen before to build some better intuition about how they're operating, and this will in turn give you a sense of when you might want to use different systems to accomplish different tasks. So in particular, looking at the frequency response.